Here, all are here.
Yeah, so Professor Kakoti is here, and a few other colleagues from other departments are here.
Yeah, good.
Students are joining.
Now, as the people come in, you have loaded this one, no?
Yes,
File.
yes, yes, yes. The PPT is with me. PPT and the small video is with me.
Pardon?
The small video that you sent me is with me. Also the PPT. So
PDF is there or not? That is more important. See, what I found was some of the text, the PPT isn't not appearing. So that's why I made it PDF, and in PDF everything is perfect.
okay, okay. PDF is also with us.
PDF. You use
Okay,
the
okay, okay.
PDF for the broadcast.
Okay, okay. Sure, 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 sure.
Okay.
We'll do that.
And it will be final Tezpur talk PDF, something like
Yes,
that.
yes, 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 yes. We have
Yeah,
with
that is.
us.
So, how old is your institution? I think it's about 20 years old, if I'm right.
Actually, it was started at 1994.
Oh, 6 years to 2000, and I am now 22, 28
Yeah.
years old.
Yes. And our department was started in 1997.
Okay.
We have now almost 17 faculty members,
Okay.
permanent faculty members, and we have few part-time faculties.
Uh-huh. Where do they find placements, jobs and all? They come to the
Yeah,
you.
yes, sir. Situation is relatively better from last 3-4 years. So now many students
And
get
mostly,
in campus placement.
okay, mostly due to one more thing is the software scene has made it much. Software,
Yes, yes.
right? Am I right? Software, because of the software, there is a lot of jobs are there. But it's a dry up.
Correct,
Should be,
correct, 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 sir.
we
Correct.
should be careful. So that is one of the reasons why all this. I, I started in 80, this having fun. And
Okay.
I said, I was watching kids who don't even know how to make anything. How can we produce good engineers in the country? So I said, let them have fun in the beginning, and those who are serious, those who have the, enthusiasm, they will automatically go forward. You can't do anything after that.
So correct, sir.
What we are doing is we will put them in a classroom and stuff them with knowledge, and they don't use it. What do they use? So,
Correct.
let us hope.
Uh,
So, yeah, it is time, I think. Yeah, you could.
Ratul, it's 4 now.
Yeah.
Yeah, Professor Kakoti, maybe just we'll wait 1 or 2 minutes because students are just joining. Let us wait 1 or 2 minutes.
Then fly this fellow. This is about 1 minute or so. I think less than a minute. Just fly him and then switch over to the PDF.
Okay.
Final Tezpur talk. So that's how. I have collected these. These are things which I have been doing over the years. Most of them I collected for the.
Yeah, sudah baru.
How is the weather?
Weather is a little cold today.
I think.
Maybe around 12, 13 like that today.
Yeah. Then how about the COVID?
Co- Yeah, COVID situation is better than earlier. Students are coming back to campus. Mostly PhD students are here, but MTech and BTech students are, some of them are here, final year students, but rest of the students, they are coming slowly to hostels. So things are improving.
Good. Not very good here. I have not gone out of the house for the past 10 days, not stepped out of the flat. So, situation, we're all getting cold, cough all over the place, and we don't know what it is. That's right. Okay, ready. I'm ready.
একটু মিউট হয়েছে ঠিক আছে পারফেক্ট সাউন্ড ঠিক আছে পিডিএফ তো কপি করে দিন একটু হ্যাঁ
So, shall we begin? I'm ready.
Yes, sir. Sir, this is Rupam here.
Yeah.
Yeah.
I
Welcome.
saw you were there all through.
Yes, sir. Yes, sir. I was
Maybe-
there for the streaming session. I was there. I was checking the streaming on YouTube.
Yeah.
Okay. So I welcome everyone, all the participants of this 5-day webinar series on electronic devices and systems. And so now I request Dr. Nayanmani Kakoti to take over the session. Sir, please.
Thank you, Rupam. I hope I'm audible and visible.
Yes, sir. You're perfectly audible and visible.
Yeah.
A very good afternoon to all present. I am Nayan M. Kakoti from the ECE department, Tezpur University. Take this opportunity to welcome you all to the first session of the third day of the webinar series on electronic devices and systems 2022, organized by the ECE department, Tezpur University. It is our proud privilege to have Professor Sipta Amarnath among us as the speaker of this session, and I personally feel glad to introduce him to you. Professor Amarnath, President of the Association for Machines and Mechanisms, that is one of the pioneering scientific associations of India, from which many other scientific societies in the country build up. To name, Robotics Society of India is one of them. He is an emeritus professor in IIT Bombay, visiting professor in IIT Dhanbad, and visiting Kanins Chair Professor in Kanins College of Engineering, Pune. Professor Amarnath has several publications to his credit and has established the Robotics Lab, the Textile Lab, and the Innovation Center at IIT Bombay. He is a consultant to several industries like L&T, Godrej, BHEL, Nuclear Power Corporation. Major projects undertaken by him include spiral heat exchanger machine for L&T, push-pull mechanisms for NPC, six-leg walking machines for the BRNS BARC, and the remotely operated robot for the Army Technology Board. Professor Amarnath was instrumental in establishing the Association for Machines and Mechanisms. He was recently bestowed the Distinguishing Service Award by the International Federation for the Promotion of Mechanisms and Machines Science. It will be a day long to talk about his contributions towards the educational growth in the country, and one of that to cite that he was one of the key person in the establishing the triple ITD concept in the India. I am sure that next 1 hour is going to be very fascinating for all of us. With this, I welcome and request Professor Amarnath to take over the platform. Sir, please.
Thank you, Professor Kakoti. Thank you. Can you hear me? Am I audible?
Yes, sir.
Yeah. I hope there is no problem hearing me. Yeah.
So, sir, shall I play the video?
Yeah, you play this movie.
Yes, sir. Yes, sir. Yes, sir.
Yeah. Sound? Yeah. Sound is also there. It's a very noisy video. Have you shut off the sound?
Yes, sir.
No, let the sound come up. Then only they will enjoy it. Yes, hardly 20 seconds. So again,
Hello.
sound. Yeah.
Rupam, you can play it again with the sound to the full scale.
Hello.
Yeah.
Yeah. Sir, was it okay? Should I?
Sound.
Okay. Okay. So I'm playing it again.
I think you muted the sound.
Uh,
Anyway, sound
okay.
is not coming.
Sir, I have switched on the sound, but I don't know why I'm not able to get
It's
it.
okay.
Okay.
Don't worry. Yeah.
Yes, sir.
You can hear now. See, this is a device built by students. I'll explain once we get into the main portion of the lecture. See the way it flies, the propellers and the way it flies. Built by students, mind you. Okay, let's go to the PDF. Let's go to the PDF.
Yes, sir.
Yeah, you can start with the PDF projection. Yeah. Yes. Yeah. Okay. So welcome to this talk. This talk essentially was conceived because I was finding very few of us can design anything, whether it is in electronics or in mechanical or in chemical or in civil. Are you able to hear me? Hello? Are you
Yes, sir.
able?
We can hear you
Yeah.
clearly.
So once I realized, that was sometime in 1980, I said, let me start asking the kids to play. Play is important and we have forgotten what is play. Let me go to the next slide. Let's go to the next slide. Next slide. Yeah. So I am calling this, title of my talk is Newton, Einstein and Michael Jackson. This is a very odd set of people I have brought together. And certiculture. I will explain what certiculture is. It is dedicated to my supervisor, my PhD, Professor Gupta, late Professor Gupta. And I am saying dream, do not borrow. We borrow everything from the West. Dream and build. Practice what you preach. This also we don't do. We preach. But do we practice? Think over. And of course, shall I go to the next slide, please? Next one. Yeah. Go to the next slide. We are a nation of 12-50 million people, not one or two. Half of them below the age of 25, all young people, lots of young people. A million engineers per annum, that's what we produce. 1 million engineers, 10 lakhs. Believe it or not, when I mean the figures I knew, but still it hits you. But we don't have a product which we can say developed by us or a patent. Yes, there are, but not sufficient. We gather knowledge and hoard it in our heads. We don't use it. We are happy with certificates. Conduct any event, students will come and ask you, will you give me a certificate if I participate in this event? So we are gatherers of certificates, just like agricultural persons are, farmers are gatherers of agricultural produce, we gather certificates. So I call it certiculture. Flowers, when they are grown, they are gathered, they are called horticulture. Like that, certiculture. We are happy with those certificates. Of what use they are, God alone knows. Agriculture, horticulture, now we have certiculture. Next slide, please. Let's go to the next slide. Yep. This is the telescope built by Newton, Sir Isaac Newton, long ago, 300 years roughly. It is there, they have kept it, preserved it. He made the lenses and the mirrors by himself with his own hands. Do we do anything like that with our hands? All of us engineers at educational institutions? Can we do it? Yes. But do we do it? No. See, there's a difference. So he built this telescope. While he was polishing the mirror and the lens, he was learning more about optics. Something which we cannot gather unless we do also similarly on our own. Next slide. Let's go to the next slide. This is a refrigerator or an air conditioner, both are more or less similar technologies, with no moving part. And they are there. We find them now even in the market with the Electrolux refrigerator and all that. And this was developed by Einstein. So Einstein was not sitting at a table and writing all his formulae. This is what we do. We spend most of our time writing formula. Whereas he was also building these things. Please remember that. He was not just writing the theories, he was also building. One contributed to the other. Next. Next slide. So convinced that our kids also can do things on their own, I called a bunch of kids. I selected them by having these are good old days when there was no projector, no PPT, no PDF, nothing. On sheets of drawing sheets, we wrote invitation to come and take part in building something. And I said, those who want to must give on one page A4 sheet on one side an idea for something to climb a tree, a machine to climb a tree. Doesn't matter whether you are from humanities or maths or whatever it is. Just give a sketch of a machine which will climb a tree. Only on one side. I won't turn the paper. I told them. 250 submissions came. They can give 2, 3 ideas, 4 ideas, that's okay, but we spent a lot of time going through them, interviewing the kids, and we selected 5 or 6 chaps. I used to get phone calls from their parents, from their uncles, from their aunts, from their friends. So please take my friend or my nephew or my grandson, like that. So finally we selected 6 of them. And this was long back, the first batch. Okay. So I said, okay, so first you go home, summer holidays, your parents will kill me otherwise. Go home, spend 15 days and come back. They came back. So what are we supposed to do? I said, you are supposed to build a machine which will go around the laboratory, avoiding people and furniture. 30, the laboratory size was 30 feet into 60 feet, 1800 square feet. Then lot of furniture, many students, it has to go around. Fine. But how are we to build it, sir? You are supposed to build it. But how are we to build it? Why should I call you, man? If I knew how to build, I would have not called you. You are going to build it. I am not going to. No, but then how do you, sir? I told them, I don't know. They gave up. They knew that I am not going to tell them how to build it. Then, within like 2 days, I called somebody who knows how to talk about creativity and all that. Gave them some talks. I don't call them lectures. Talks, half an hour talk, half an hour. Then now your headache. Build it. 1 month or 1.5 months later, this was the machine that came up. Crude, but in my eyes, the most beautiful machine one can think of. Built by kids who had no experience of building anything. They made it. They use the remote of TV remote. There's a light beam which comes out of the remote, hits something on the TV, and then the TV decides which channel and all that. So you change the channels by hitting that. Those, you can see them here, small blips. Those set off the light, another one received the light and made sure they don't go and hit furniture or a human being who is moving around. They will. Where did all this come from? Where is the money? I said, in the laboratories, if you go around, you will find lots of discarded material. Bring it. Let's put it together. Let's see if we can make with that. They were excited. That's it. It came out within about 2 months. I even now recall the names. All those fellows. Of course, like everybody, they also went to Berkeley, to MIT. That's another story. Next slide, please. Yeah. Then the local colleges came to know. They said, sir, we want to participate. Then I began what is known as the Tech Fest, because I couldn't handle the numbers. 200 machines turn up. How can I handle it? I said, so we gradually moved to something called Technology Festival, Tech Fest. That was the first Tech Fest. An arena the size of a dining table, 6 feet roughly. One goal post on this side, another goal post on this side, One machine, your machine on one side, my machine on the other side. Okay? Size of the machine, it should not exceed a shoebox. That's simple rules by which we can immediately judge whether the machine is admissible to the tournament or not. And they have to play football with ping pong balls. Instead of one ball, 11 balls, and instead of 11 players, one player on each side. And play. Come on, play. Ideas come out like crazy. And they're all young people who have never done anything like this, and so they came out with fantastic ideas. Here is one. On the top right, you will see there is a tree. The tree is made out of wood, and there are branches made out of aluminium, 2 aluminium rods. And from the branches, there are threads with, what do you call that, beads hanging. You can see the red bead, one green bead in the background. There is grass around the tree, that white, the grass. Build a machine which will pluck these fruits, take them to the corner of the ground and put them in a hole. Rabbits gathering fruits. So it was called Bunny Rabbit. The game was called, you give fancy names, that attracts the youngsters. So they made all sorts of funny things, you can see that. Then I challenged them, without electronics can you make the same one separate section? I said, without electronics. You can see at the bottom on the left, the machine had one running, it will hit the vertical base of the tree and then open up, go back. If you let the kids work, they will learn by themselves through their mistakes. We have forgotten this. God knows why we forgot. Totally we have forgotten this. And we take a stick, sit in the classroom and make them do writing equations. Next. You think only Newton and Einstein did things by themselves? Michael Jackson. Somebody whom all the kids love. Zing bang. Music. Here the whole troupe, dancing troupe, is bending forward at an impossible angle. They can fall and break their noses. For this dance, the shoes were invented and designed by Michael Jackson himself. You need it, you do it, you make it. That should be the philosophy of our kids also. Do it yourself. DIY. And if you go and look up, I won't tell you, how many patents did Einstein hold, you will be astonished. Well, everybody knows of him as somebody who wrote all the equations in the world. No, he was not sitting in a corner and then mooning about theory of relativity, stars and all that. He was making so many things. Next. So what I did was design exploration workshop, I used to call it. I used to call the kids, tell them, construct elements and subsystems, free wheels. Cycle free wheels. They make them out of any material you like, whatever you find, discarded material in the laboratories, in the workshops, or you go and bring, but you can't buy. With marbles and what is known as mount board. If you go to your grandfather's house, you will find on the wall photographs of his family. Board is different from mount board. With that mount board, they made cans, gears. I'm talking of mechanical. I'm sure there are many electronics and electrical people here. We'll come to them also, don't worry. Then, understanding material. What do? You take them to your center of material, some lab, there's a machine, you put a rod, you pull, it breaks. Have you understood the material? God knows. So, bring 5 types of coat hangers to the classroom. Okay, I'll give you half an hour. Break the coat hangers into as many pieces as you can without the help. There are no vices, there are no, what do you call that, hacksaws, nothing. With bare hands you have to break them. You should see the illumination that comes up when you do this. Some of the students had brown lines on their fingers because when they were trying to break up the aluminum or the steel coat hangers, they were getting heated, internal heating. And that was creating those brown welt, W-E-L-T welts on the fingers. They will never forget internal friction in their whole life. Use of tools was not permitted. 1 million uses of a pencil or a chalk piece. You ask them 1 million uses of a, somebody asked me, why 1 million? I said, okay, if I ask them to give me 50 ideas for use of aluminum foil, the ideas come like this. Wrap a vada, wrap a dosa, wrap an idli, wrap samosa. Each is one idea, sir. So don't tell us. But basic ideas what? Wrapping. I want 100 types of ideas. So when you say million, they don't know what to do. Get them. You see? Give them challenges. For example, one of the greatest challenges in our country is the bolakat. The bolakat is locally made, material is local, skill is local, people are local, education is local. Make it. And it works. Whatever be the shape of the road, it may have all sorts of deformations on the road, the bolakat will go. Have you ever thought of it? What a great invention it is. Everything made locally. Now where aeroplane, you go to US and buy, or you go to UK and buy, or you go to Russia and buy. No. Made in your backyard. Elegance. It's a very elegant product because utility is great, complexity is less. See how elegant that product is. We have ignored all that. So then I started promoting dream projects. We'll see that later, the picture. Then senior students mentored the younger lot. Like for example, the machine to climb the hill. So one day what happened was, the senior students came to me and said, sir, you should take rest. I said, why? You have been running these things for a long number of years. I think you take rest, sir, we will conduct. I said, fine. So they came, they started conducting. I didn't go near the room, I was away. Next day, they met me and they said, sir, all these students are dumb, sir, useless fellows. I said, why? Said, because they are not excited at all. I said, what did you do with them? No, sir, we told something. I said, let me come. Then, there was one manufacturer of this, mechano sets. He lived in Bombay, where IIT Bombay is. He somehow liked me, or he fell in love with all of us, me and my students. He gave us bunch of mechano sets. 24 mechano sets he gave. So what I did when these fellows told me that those boys are zero, I took the mechano sets, some 3 or 4, went to the classroom where they were all sitting, dumped them on the table, and then see that hill there? Yes, sir. Build a machine which will go up the hill. Next morning, I met the senior student. Sir, how is it going? Sir, fantastic, sir. You came and said, build a machine which will go up the hill. They all got excited. And that is the key. You have to excite them. Okay? Now, let me go to the next slide, please. Kids playing water polo. This is a tank, acrylic tank. Water is there, and there are ping pong balls. See the way see the crowd and see the way they are playing. This fellow hung the machine, the controller around his neck, and the machine is in the water. Why? What is the challenge here? If you are not careful, the machine will burn up, or you will get an electric shock. What I found is 3 exercises you have to. First exercise is scrap. Scrap only will come. Don't worry. They'll come back for the second one. They'll do it. By the time they come to the third exercise, you'll start seeing the gems around. Beautiful ideas. And some of them are hooked onto it. Innovative abilities surface. Talents are discovered by themselves. You are not doing anything. Teachers think they are doing a great job by discovering talent. No, it is not the teacher who discovers. They discover it themselves. Remember that. Next. 3 exercises needed before you can. Where does all this lead to? What extent can I go? Sit. Here, this exercise I used to call it as DEW, Design Exploration Lab, workshop. Explore design. What I used to do was I used to call about 30 to 40 students. I used to, all over the campus, hang cardboards with some challenge, ask them to give 1 page. Yes, 1 page only, write up. I won't turn the paper around, I used to tell them. Select a few, they will come. Keep the institute bus ready. It can load about 25 people, plus 2 or 3 seniors. Put them on. Tell the driver, go. Some 4 hours, 5, 2, 3 hours you drive. Every 2 kilometers you drop some 4 students. Go to the next spot, drop another 4, like that you go till you reach the end. Wait there for 1 hour or 1.5 hours, then come back collecting all the students. And what do the students do? In the meantime, they talk to the common man, the taxi driver, the rickshaw puller, anybody whom they meet. The fellow who is making vada on the road. Let them talk. Come back. 2-minute presentation of what they saw. I am no longer giving the problems. They are bringing the problems. You see, no, they own it. It is theirs. Within 1 hour, they have spoken to each other. This was one on the left-hand side. That was, and then as it started maturing, I used to say anybody can take part, not necessarily first year. That boy with the cap is a PhD in mathematics. It's all very old stories, of course. Mechanical engineers, electrical engineers, metallurgy, the whole gang was there. What is this? I asked them, what is this? What did you decide to build? This is indoor games for the visually handicapped. There are no indoor games for the visually handicapped to play. Did we ever think of it? We never thought of it. So you have to go and scout for problems, not just sit in an armchair and say, oh, this problem, Karo, this you do it. No use. So what is this game? There are 4 staircases, one from north, one from south, one from east, one from west, going to the top of the hill, made out of acrylic. Steps. You go up. Similarly, you go up. 4. In some of the steps there is a hole. So you throw the dice. If the dice says 3, you move your marble up 3 steps. But if there is a hole there, the marble will fall into the hole and come back to the bottom. What is this game? Snakes and ladders. They made it. It's stunning. And we go all the way to US and UK and all and borrow those games. All here. What have they done after this? On the right hand side, what is the purpose of all this? Excite them into building things, into developing things. What are you seeing on the right? The devices they made and their marketing. What is the device? See, by going and scouting for problems, they woke up. They realized that problems will not come to you. You have to go to them. So what is this? Guitar, acoustic guitar. Not very expensive, but the electric guitar is costly. So they made a patch. You stick it onto the acoustic guitar, it becomes an electric guitar. So they have an idea. I never told them. If they used to come to me, sir, give us some ideas, we get lost. My ideas will be foolish. You go and you find your own ideas. And it works. Next. Next is, it's not for kids alone. This will go in and you will start doing things which you never thought you were capable of. This is the awakening, waking you up. Nuclear reactor, inside of the reactor has to be cleaned. There are 1,000 tubes whose insides have to be cleaned. Each tube is 200 millimeters inside diameter, and roughly about 20 meters long, 15 meters long. And once in a blue moon you have to clean them. But you can't go near, the reactor is radioactive. You will die if you go near. 1 minute, 2 minutes. So they came. Can you do something? To cut a long story short, I told them yes. See the size of the reactor. Can you see the human standing in the picture? The top left picture? So that's a massive. Each time the devices they built, they cleaned one tube, they had to bury the device because whenever a device is used, it becomes radioactive. So you have to bury it, you can't bring it out. These are real life problems which we never come across. We are happy with our equations. Next. But they are needed, don't neglect. Just because I am making fun of them doesn't mean you should neglect them. They are also badly needed, you will see. The mean time between failures of infinity was demanded. That means between two failures, the amount of time must be infinite. This is called MTBF. Engineers will know this. Next. Yeah. So, can you go back? I told the students you go through brainstorming. Somebody said, sir, why not just use like the maid servant at home who cleans the in your kitchen there is the drain. It's a pipe. It puts the jar inside that and then keeps pulling back and forth. Why can't we do like that? That's what. Such ideas came. But we have to convert it into a machine. And the machine should not fail. What to do? Next. See, the movement of the arm, you can see C1, C2, C3 are the curves along which the arm tip is moved. This is arm mechanism. You see a sort of a D-shaped curve. One straight line portion where it is pushing the and then go up, release. Next slide, please. So one of the students told me, हम बनाएंगे एक, बनाओ. He is pulling a wire rather than pushing a huge 200 mm diameter pipe, 20 meters long. You can't do it in the lab. So instead he showed his idea on a wire. This wire you can recognize is the same wire as the brake wire, which you use in your cycles. Go and use anything you like as long as you can convey the correct. Instead of crying and saying, you know the story of the fellow. The family goes to the thieves rob one little kid because he had the ability to climb the walls of the fort. So they catch him and take him there. They want him to climb the wall of the fort with a rope, throw it inside, they will all climb and rob the fort. The king's palace or fort, whatever you call it. They take the kid there. Then he says, you play this music, you play, my mother should dance, my sister should play the drums, my father should play the flute, then only I can climb the wall. That won't do, my friends, in modern day. Senior students also told me, sir, ask the younger students who are doing all this to make a drawing. Drawing is something which every one of you hates, I know it. So I asked, did you ever draw? You made so many things. Did you draw? No, sir. Then now why are you telling me to tell them? You tell them. Because the senior students have realized the importance of drawing. That is the first soft model of your idea. Then comes the 3D models in the computer and all that. I was happy because they had thought of this, that drawing is required, not me telling them. Let's go to the next slide. See this one. This one, that student I used to, he is now, the student who built that, he is now chairman of a big company between Pune and Mumbai. Okay, next. Now this one. This is the actual machine which we use inside to clean. This is the actual machine. Built by one of my students who passed out long back. I called him. Said, can you make it, man? They are ready to pay. Huh? Then he comes and tells me, how the hell did you think of it? How did you think of the whole device? Because I was working with my hands right from childhood. Next. So see, these girls, they had gone to a hospital to see what's going on and they come back with problems. They have depicted the problems on a drawing sheet. What are the problems? The problems faced by people who are bedridden, how to clean them, how to brush their teeth. So many things have to be done. If you draw this, what is known as a storyboard, you don't miss the points. Otherwise, you miss half the things. You make it, this is no use. Okay, next. There is a sense of ownership. You are nurturing Continuity is there. Next year, that sheet I can pass on to another batch. Tell them you take off. Their attitudes change. They are liberated. Okay. Next. This is a pipe climber made out of scooter tires. Cost it about 200 rupees, I think. 2 balloons at the end. One balloon will, you push it into a pipe, one balloon will grasp the inside of the pipe, or rather push both into the pipe. One bottom balloon will grasp the inside of the pipe, then the top is this, what do you call that? Bellow is then energized, it will push the top balloon up. There, that top balloon will catch the side of the pipe, and then the bellow will pull the bottom balloon up. Like this, it goes on climbing. Simple. 100 rupees. Why? They wanted it because once they use it, they have to throw it. So we made it for them. Students, don't worry. Yeah, next. You have to play, fun. There's a lot of fun. But don't think there is no theory. I'm showing you the fun portion. Now I walk into the unknown. Mechanical logic gates. Just have a look. 0, 0, the output is here 0. 0, 1, output is still near 0. 1, 0, same story. 1, 1, the output goes to 1. AND gate. If you want to have this sort of a device in a bulldozer or a construction machine or any heavy machine, then what do? You need a motor, servo motor, then you have sensors, and the sensors you get you sense where the device is, then run the motors, move it forward. When both move forward, the output moves. Whereas here, no sensors, no electronics, nothing. Directly you get it. A mechanism being used for generating the logic of AND and OR. There are a lot more devices which I have made. They are also there. Hey, you have fun? Okay. The trouble is, I should allow you to fail. Failure is a stepping stone to success. If there are no failures, there are no stepping stones. Where is the success? Keep that in mind. Okay? And you will find, those of you who are doing theory of machines will find higher pair, lower pair, words like that sprinkled here. You can't avoid the theory. You start appreciating the theory. I hated theory of machines. I ended up doing a doctorate in that. All because I did something with my hands. Next, we're more or less coming to the end. If you cannot make it, you perhaps do not need it either. Remember that. If you need it, like Jackson, he needed his troop to move, bend forward and not fall. He made the special shoes which permitted that. He is dancing and then suddenly at one spot he locks the shoes to the ground, bends forward. He needed it, he made it. Do we do that? So please keep that in mind. Please note that you have, if you need it, you must be able to do it. Einstein did it. Newton did it. Michael Jackson did it. Why can't we do? That's the message I propose to convey to all the young people. Don't worry. 3 failures, 4th one will be a success, surely. And let it not be just mechanical engineering, because I being a mechanical, I take those examples, whereas it could be in electrical engineering, it could be in electronics. Okay? So with that I close and thank you for your patience. I hope you enjoyed it or you liked it. Even if you disliked it, I can't help it. Thank you very much. Yeah.
Thank you very much, sir, for
Any
your
questions?
insightful talks and the clear message that can we do it? Yes. Do we do it? No. I think it is a very impactful message that your deliberations has taken to our students. If they think deeper on it, I am very sure that they will be greatly beneficial.
All of them can do it. I'm 100% confident. You know, all of them can do it. There's no worry.
So, Ratul, would you like to brief something over here?
Pardon?
Yeah, yes, sir. We have a question
Yeah.
from Quaho Roberts from Africa. So he's asking, sir, what can you advise for someone who is very innovative but lives in a village where technology is not embraced, and every time he comes out with something, he is instead discouraged?
That is true. See, this is the tragedy of our countries, you know, people discourage. Now things have started changing in India, as you are able to see now. They are giving, let him build and exhibit. That's what I found is the best. I used to get the students to build and exhibit. Many of them have taken off. Build and exhibit. And don't bother about how much is the cost. Even if it's a mock-up, because anyway, the cost is a big headache. You don't have money. I used to tell students, go around the institution or the college, whatever it is, pick up things which have been discarded. There will be many things we have been. We built a boat, okay, out of what was essentially, it was something to carry firewood. They had built a carrying device. So it was used once or twice and then left like that. That we borrowed, we built it, we remodeled it. Like that, you know, we did so many things. So you have to improvise based on your own thought process. You have to come up with ideas and you will gain a lot. There's no worry. See that first machine I showed where the pieces borrowed from remotes of TV. TV remotes were borrowed or broken TV remote. So they use like that, you know, you have to keep on looking, and believe me, once you start looking for them, your brain will always be looking. One day one student told me, sir, you told us how to go around looking, now I can't stop looking. I keep going around looking only. I can't stop looking. It happens. It's okay. So you will enjoy. There's no doubt about it. Even teachers will enjoy. It's not just the students. Everyone will enjoy. How many students do you have on campus?
Probably for
4,500.
engineering, yeah, around plus 4,000.
Yeah, it's kick off. You don't lose anything. And what? See, the most important thing that happened in IITs was a regular timetable. In IITs, winter 1 month, December, no classes. Summer 3 months, no classes. 2.5 to 3 months, no classes. So I used to tell them the lab doors are open, come. I used to go to the laboratory at 10 in the night. I'll just be wandering around. And somebody asked my wife, where is this fellow? She will say, you just go wander around, you will catch him, don't worry. You just be walking around. Some students will come, sir, this we have. One day, I went home around 8:30, dinner time. My wife said, those started crying. Because we had internal phones on the campus. You know? So from the laboratory they had phone and they were crying. She said, I could feel they were going to cry. I said, okay. I had my dinner and then I went. When I went there, they were sitting in the front of the department, some 6 or 7 fellows, and they were virtually in tears. I said, what's wrong? Something. You know, at that age you cannot communicate. You still don't have the ability to properly communicate. So I said, okay, let's go in. We went in. I knew where the solution was, but I didn't want to tell them. Went around, saw that, saw this. Then one fellow suddenly discovered something. Sir, this will solve my problem. I try it. I never say, yes, try it. That way, you know, slowly within a few days, they become adept. One day one fellow comes running. Sir, you wanted us to go for this? That you saw that game where they have to play underwater, they have to play water polo. Half the machine will be underwater. So, how to keep the motors from getting damaged? I said, I don't know. Then they said, in those days there was no, what do you call that, on your computer you have this, no? Google. There was no Google. We had telephone directories and we had some booklets which will show you where in which shop things are being sold. That's all. So they found one. So there is a shop which is selling water seals, SEALS. That's the correct word. I said, go and find out. So they went by bus, they went there. That fellow asked, how many seals do you want? This fellow said, 2. Only 2? Okay. It pulled out a bunch of 25 seals, put it on the table and told them, you take this. These fellows were stunned. Actually, what was that seal? That was the seal that is used to keep the injection bottle has a rubber cork. That rubber cork, and over that rubber cork there is a seal which is made out of thin aluminium foil. You have to tear it, then you can poke through the rubber with your syringe and draw the medicine out. That was the seal that fellow showed. So then they realized, sir, we didn't know how to tell him. And said, no, I think it's partly our fault. We spoon feed them, which is not right. We spoon feed them. That's not right. Just leave them. They'll come back. Yeah. Any other question?
Sir, one of the participants, she is asking that, sir, sometimes we do work, but neither we fail nor we get any output. Then in that situation, how to continue the work and stay motivated?
You have to push yourself. There is no other way. You have to push. And anyway, you will find some friends. They will say, why don't you try this? Why don't you try that? Try that. It will work out. They say, there is never going to be a failure. Whatever failure is there will be, that's what I said. To I found that two exercises, third exercise you do very well. Third exercise I found usually the students do very well because they have learned from the failures. So there is a lot of learning in failures. Don't neglect them. Don't neglect failures. Present it to your friends. That's why that presentation is important. Many things I used to have weekly the students building something. One day one boy built a snake. Then I exhibit it in the corridors of the department and invite anybody and everybody. The worst are the school children. Because the campus, it will spread, word will spread. School children will come. God help you fellows if the school children turn up. You can't answer a single question what they ask. They will make your life miserable. That's how you learn. Let the kids come, the small kids will come and they will say, sir, if you do like this, it may work better. For all you know, that might be a good idea also. So don't worry about failures. That's what I'm trying to tell you. Don't bother about failure. Keep doing. And you have how many? 4 summer holidays you have, right? And begin in the first year. By second, third, if you don't begin, you have lost them. They won't come back. That's what I found.
Thank you, sir. I hope, Rupam, do we have more questions or?
Sir, we do not have any more questions now.
Okay. Actually, we had a couple of questions in mind, but keeping time in constraint, I'll keep it for no future lectures or future interactions with Amarnath, sir. So thank you very much for taking out your time to spare with us and giving us the valuable deliberation. And one thing I would like to mention over here that yes, the country now needs to come out of the certi culture. And we have started a very small step towards this called the RoboAnalyzer based online competition. In that competition, we give the theme of the problem to the student, and whatever they do, they got award based on that, but they do not get a certificate. There is no explicit certificate policy. Whatever work they do, we record them and we put it to 2 websites. One is to Tezpur University websites, one is to IIT Delhi website. So 2 institution websites are saying means it is true. The whole work is we preserve the students' work.
I'm thrilled to hear this because I never gave a single certificate.
Right, sir.
Never gave a single certificate. And they are all doing well. What more do you want?
Right. So thank you very much once again, and it is really nice to have you among us. We wanted to continue with you more, but because of the time constraints, I think organizers will now go to the next. Ratul?
They have another talk after this. I know. I saw it.
Yeah. So thank you so much, sir, for joining us and readily agreeing your for the talk. Thank you so much. So we hope you will join us in near future again. Thank you so much, sir, for your time.
Okay. Thank you. Thank you, one and all. Yeah. Bye.
Thank you. Bye bye, sir.
Bye.
Thank you, sir.
Good afternoon, Akhtar sir. Can you hear me, Akhtar sir?
Hello.
Yeah, can you hear me?
Yes, please.
Yeah, good afternoon. Good afternoon, sir. It's after a long time we are meeting. So for those who do not know, sir, he came to our department and he stayed with us for 2 weeks to develop the Mams laboratory. So thank you so much, sir, having you again. here in this platform. Now I request Dr. Kakoti to continue with the session, please.
Yeah, thank you, Ratul. So once again, good evening to all and welcome back to the second session of the third day of the webinar series on Electronic Devices and Systems 2022 organized by the ECE Department, Tezpur University. It is our proud privilege to have Dr. Jamil Akhter among us as the speaker of the session, and I feel glad to introduce him to you. Dr. Jamil Akhter started his career with Bell, Ghaziabad, and working through various positions in research and administrations. He also officiated as the director CSIR Seri Pilani. He was associated with ACSIR New Delhi as professor and has coordinated Advanced Semiconductor Electronics course. He has been instrumental in imparting hands-on training in Mams and NP-MAS program to the faculties from engineering institutions and universities. He holds many patents to his credit and more than 200 papers in journals and conferences. He is a senior member of IEEE USA and member of International Solar Energy Society, Germany. He is honorary member of Chemical Society of Georgia. He is an awardee of CSIR New Idea Fund Project Bharat Shiksha Ratan by Global Society for Health and Education Growth, New Delhi, Bharat Jyoti Award by India International Friendship Society, New Delhi. So if I go on, it will be a long list to describing about Dr. Jamil. So to end with Dr. Jamil working as a director of the School of Electrical Electronics and Communication Engineering, Manipal University of Jaipur after superannuation from CSIR Seri. So it is our pleasure to have you among us in this evening. With this, I welcome you again and request Sir to take over the platform. Sir, please.
Thank you. Thank you, Dr. Kakoti. So, should I start now?
Sir, please.
Okay. So, let us check whether actually slide what I am having here will be okay or not. Otherwise, then I will request my PDF file may be shared from there. So let me check first my PPT. If I share from here, then it's okay. So yeah. So maybe Dr. Kakoti, if
Sir, could you find
if it is possible, you can share my PDF from there.
Okay, sir, could you find the share option?
Yeah, I have not found that option here.
Sir, there is a below the screen. There are some round buttons, and there is a square one with an arrow inside it.
Yes, it is there. I did it. Then a window. Okay, he's asking for a window.
Yeah, you can select your entire screen, the first one.
Acha, entire screen. Okay.
Right. You click on the entire screen,
Mm-hmm. Then
and
share it.
then you have to select the window, the screen that is appearing on that window. You just need to click it on it, and then a blue boundary will appear. After that, you can share. Click on the share.
Yes, actually, it is not taking that screen where the PPT is. So it is going some other window.
Okay. In that case, then you can send me, sir. I'm sending the email ID. Probably you can have my email ID in the search box. Yeah, please send the.
Ratul.
Yeah.
Ratul, possibly sir got disconnected.
Yeah, he got
Call him.
disconnected. Yeah.
You can call him. In the meanwhile, if the participants know if you have anything to interact with the faculty members present over here, you can do so, please. I could see there is around 38 students joining us, but all are with the webcams off, no? You're just listening? Can anybody listen to me from the students? Can just say and hi, good evening.
Yes, sir.
Something.
Yes,
Good evening, sir.
Hi, Kavita. Hello. Hi.
Good evening, sir.
Hi, Bhargav Nath. Akash. Hello,
Hello, sir.
Anisha.
Hello, sir.
Are you people just listening, keeping your mobile side or doing something else, or you are really no enjoying the talk, attending the talk? It can happen anyway, no? You can just keep your mobile, joining the session, and then there is no harm in doing anything, whatever you are doing. And just for the sake of interaction, saying, can any one of you switch on your webcams? No. And then I can see Bhargav, Anita, Krishna. I can see now switching on the webcam. Yeah, people see when somebody is talking to you, no, over the webcam, and you are keeping your no, it is off. Then people feels we are talking to the machines. One way we are anyway away from one another, and that also we are keeping ourselves completely blocked from the outside by keeping the webcam off. No. When you are on, it gives an no, although you are not talking, there is a sense of no interaction, more interaction. Okay, good to see a couple of people switching on their webcams. They're and joining for this talk. Have you enjoyed the talk by the Professor Amarnath?
Yes, sir.
Very good, sir.
Right. It is basically for you. See, the Ratul sir and Rupam sir is taking so much of pain, no organizing and bringing these well-known personalities who are now across the globe known very well. So take the benefit of it. And even if you are not taking the benefit, then it's up to you, whatever you want to do. But if you are here, no, please, with your complete mind. Hi, Nivedita Talukdar. In the meanwhile, Rupam, could we connect with?
No, sir is disconnected, so I have sent him the email. He
Okay.
will send the PDF now.
Okay.
So I think he has some internet issues.
All right.
So let us wait for a few moments.
Sure. Sure. Hi, Bhaskar Jyoti Barban. How are you?
Yes, sir. Fine, sir.
See, we all are in-house people, right? You know at least me, na? Ratul sir, me, Rupam sir, right? You people know us, no?
Yes, sir.
Yes, sir.
Now I am afraid.
Yes, sir.
Okay, because yes, sir, I can hear only from Bhaskar. Others don't know us. Is it?
No, sir.
Okay.
We know you.
Okay. Yeah. See, you can ask anything. Don't be so within a small cocoons. No one is going to say you anything. You can go as you like. Hi, Brijesh. How are you?
Sir. What about sir? What about you?
I am good. Only with my 2 ankle bones broken. Otherwise, I am very good.
How, sir?
Some incident happened.
Oh,
Some incident happened. So,
basically, sir, I'm connected with 2 systems
okay.
because my laptop camera is not working. So
Okay.
that's
Okay. Okay. All right. So the last talk was interesting, right?
yes, sir.
Yeah. There is another thing. This group of people, Association of Machines and Mechanisms, they do it RoboMuse. You make some machines, and then they will make a cubicle or some space in the institute for you, and your machines has to keep on running continuously, day after another. So that way, if you develop something, then when you run it for a long time, you come to know what are the advantages, disadvantages it is having, and then again you go back and work on it. That RoboMuse is another very interesting thing that they do. You people can also come up. How many of you are in the 8th semester here? How many of you people are in 8th semester here? All from MTech and PhD. Oh, I think sir has joined.
I'm sorry, actually, because you know that browser actually it does not accept other browser other than this Google Chrome.
Okay.
So
No,
that's
sir, not a problem at all.
Yeah.
Not a problem.
Let me off this my phone.
Yeah, sir.
Please. So thank you for the patience. Actually, you heard. Okay, let us start. In this talk, actually, what I planned to share my experience on developing the Mams-based pressure sensor. Though we developed very dedicated pressure sensors for certain applications, but actually I thought that from the technology point of view, only if I see, then there are variations in that, and that is the main purpose of this lecture, that how the technology actually will influence the performance of the device and what are those rules of the technology. So I will discuss here only those 3 rules actually based on the basic material what we are using to make this pressure sensor, and how actually it will give us the different sensors with varying performance. Okay, so coming to the next one, first actually after retiring from CDP learning in 2019, next slide please. I think I am audible.
Yeah.
So next slide please. Yes. Okay. Actually, here briefly, 2 minutes I will take that. Now I am here in Manipal University in Jaipur, and this university was established in 2011. Very young university, 10 years over now. And during this time, this university has got NAC A plus also, and other accreditations, and more than 10,000 students are registered here, and more than 500 faculties. Next slide, please. So, I'm sorry, I will request again for the next slide. So this is the basic structure of this university here. From the academic point of view, there are 5 faculties here. If you see that in the inner circle, Faculty of Science, Faculty of Management, Faculty of Design, and Faculty of Chemical and Civil Engineering, then Faculty of Faculty of Engineering, and under these 5 faculties, you will see each faculty is having different schools. For example, FOE is having a School of Electrical and Electronics and Communication Engineering. So I am here. Each school has its own director, and then under that one school there are different departments. So for example, in ICC there are 2 departments, Department of ECE and Department of EE, Electrical Engineering. Similarly, in SAM, that is Automobile, Mechanical and Mechatronics Engineering, there are 3 departments, and so on. So this is and you will see that here in this university, it is Faculty of Science is there, and Law and Management is also there, and Arts, and other departments of humanities is also there. And they are also planning for the medical sciences here, and you will see, I have seen here from since 2019, though 1 year I spent in hospital because of my ill health, but I am very happy to be here, and it's very good environment. And now the university is planning to have a research university type of culture in this university. And so this is the basics. And of course, this is a private university under the Mahe group. If you know that in Karnataka, there is the Mahe group. And Manipal Academy of Higher Education, this is the full form. And Institute of Eminence actually has been given to this. Next slide, please. Can I change my slide? I think I...
Yeah, just a moment, sir, just a moment.
So, Dr. Goswami, I'm just... Okay. Next, yes. So, basically, I will try to finish in time. So, let us actually discuss what is the basic, actually, which is very familiar structure of pressure sensors. So this is the cross section, and so cavity is from the one surface side. So this is based on anisotropic etching. So here also variation in the technology also introduced here. So I will just try to focus that what are the different actually sections in making the pressure sensor where technology variations are there. You can make by some conventional techniques. You can also use some new techniques, and the accuracies, the shape, and other things actually. And on the other side, if you see that sensors film, which is the sensing material, how we can deposit, whether we fall for one technique or another technique. So I will discuss all that. So here actually this is a typical sensor chip based on Mams technology, where the cavities form on the other surface, and on the front surface, the sensors are placed on the diaphragm, and then further connections are there. So this is a kind of an introduction of a sensor chip. And based on that, next slide, please. Can you go to the next, please?
Yeah.
So this is the array of the chip, actually what I have shown in the earlier slide, 9 by 9 matrix of the pressure sensor of one surface. You can see the sensor, this piezo resistors in the form of the wheat-stone bridge configuration on one side, and on the other side, backside, you can see here in the second figure where the cavity has been formed by anisotropic etching of silicon. Of course, anisotropic etching of silicon gives you a very accurate structure, whatever is designed, but of course, this is a chemical process, and some variations is also there, and I will also discuss on that. Next, please. So these are the typical pictures of some of the devices. So chip actually is bonded on such kind of package, and then it is completely sealed, and then pressure is applied in the form of this outer package, you can say, and these are the typical performance. So if we apply the pressure from the bottom side, or we apply pressure from the front side, both way, and the device works. So this is the general thing which is very well known to the person actually who are working in this area. Okay, next please. And once actually this device is packaged, and in the packaging form, after that actually the required electronics is interfaced, and then the application is done. And I am proudly say that this was developed by one research MTech training from Tezpur University, and this photograph actually, of course, this is the contribution of Tezpur University also, because one of the trainees actually he did this work during that time. So basically now, what is actually going on, that this readout electronics, it is miniaturized, and the whole thing actually can be housed in a simple package, and this further miniaturization, which is possible, and people are working on it, and people have produced these in the market also. So this is the thing, and I will say that sensors are available, individual sensors are available in the market, people purchase, but necessary electronics for a particular application. This is actually really a work which is not easily available to our industry in the country, and it is better to train our young minds actually to design this readout electronics, which is application specific, and this should be actually interfaced with the sensor. So generally, what we do in the lab, we if we are developing a sensor, so we are up to the stage of the sensor making. But how actually to develop the required electronics, so it remains again actually a work which is left, and the whole technology actually not possible to transfer to the industry. This actually we have seen during my tenure in CSIR series, that we were having the sensor chip fabrication technology, but depending on the applications, the required electronics, though we understand that it is very simple, can be done, but actually the whole technology should be available. So that's why actually we tried to make the working prototypes, though it was a big in size, ECB was there, and I tell you this was done by the trainee actually, yeah, and so it is not that difficult. Anyway, next slide, please. So these are the further photographs of the conventional Mams pressure sensors available, and if you see this photograph where the pressure can be applied from the backside, or vacuum actually may be actually measured through this chip, because if we are applying vacuum here, so it will suck the diaphragm, and similar behavior of the sensor actually will be observed as the pressure is applied from the top side, and so on. So packaging of these devices play a major role, how to actually use the chip for what applications. Next slide, please. And here actually I show you some of the packages for different applications. For example, if we want to use the same chip to measure the pressure of a liquid, for example, the water pressure, or some actually corrosive liquid also can be used. In that case, we have to use these things, components of the package compatible to that particular liquid. So this was especially for the water pressure measurement, because for drinking water systems and DI water plants, there was a huge demand of pressure sensors, and some work was done to develop the package so that actually they could use it. And you can see the different type of packages actually for the same chip actually. Chip is same, but package actually decide where it will be used. So that's why I put here application specific package modules. On the right side actually picture, this shows that the stainless steel packages were developed for the same chip to measure very low pressure or very high pressure actually. So up to 200 bar actually these packages, they could be used to measure this high pressure and high temperature sometime also, depending upon that chip, and the chip fabrication has been done according to the requirement of the high temperature. So and this high temperature business this actually brings a change in the technology. So I'm coming on the main topic for which actually I plan to share this knowledge. So packages actually, this is also equally important activity in developing the sensors. So if we are good in making the sensors up to chip level, but actually we have not worked out, or we have not involved the competent people who could actually think for the packages, then perhaps it will be difficult to take the technology out from the laboratory to the industry. So I think this is also important aspect, and we should also work for that. Next slide, please. Okay, so now coming to the parameters which actually bring a kind of a change in the technology. And why actually we use the different technologies? Because of the ease in the fabrication, of course, because of the cost, because of the large scale fabrication, pilot plant or something like that. So to bring the cost down and the repeatability and other things. So now actually these are the various changes in the technology where actually we have to decide after that which technology we should actually bring to the industry and establish. For example, from the substrate point of view, should we take a very high resistivity N-type silicon? Because we know that cavities form in crystalline silicon. And silicon itself also is a piezoresistive material. So if we are having the very high resistivity of the order of kilo ohm centimeter or something like that, and it is N-type, so because this also has a meaning that it should be whether N-type or P-type. So this will have a different route of making the pressure sensor. So here, if we want to make the diffuse resistors as piezoresistors, which will be the part of the diaphragm, so this will have a different performance. I will just give a hint that from the noise point of view and from the stability point of view also. So you will see that if the requirement is that you have to have the sensitive part or the piezoresistors of crystalline silicon, then you have to have a diffuse resistors in silicon diaphragm. And for that, because if you are making a resistor in a substrate, then it should be isolated also. So generally, piezoresistors are made of boron doped or P-type silicon. Then your starting material should be N-type silicon, and it should be high resistivity because the crosstalk between the resistors should not be there to avoid it. And so this will make the change in the whole process actually. Another thing is if we are having the silicon as a material simple, we are not bothered about whether it should be N-type or P-type. Then the simple thing is that you have to have the polysilicon based piezoresistors over the silicon diaphragm separated by an insulating layer deposited by thermal oxidation process or by PCVD process, but the quality of the oxide should be good. In this case, the resistors will not be the part of the diaphragm. It will be externally placed over the silicon diaphragm, and the separation will be, isolation will be through the grown silicon dioxide. So here actually we can play with the silicon dioxide, how much thick, what is the quality of the silicon dioxide. As in the case of the diffuse resistors, the quality of the one-sided abrupt junction, actually that will decide that how the crosstalk could be minimized. Similarly here, the quality of the silicon dioxide actually will decide how we can make the individual resistors isolated or minimize the crosstalk. And the quality of the silicon dioxide, which is a very important microelectronic process. So the overall cost actually of the process actually will be down here and will be very cost effective and easy to fabricate. In SOI based process actually, if you are having the substrate where silicon on insulating substrate it is there, so everything actually is ready, that your base silicon is also there and the very fine quality of oxide is also there. Over that, you are having the required sensitive layer of crystalline silicon again, with required resistivity and the thickness. So very high quality substrate is there. Only you have to define the resistors at the desired locations, and then metallizations and other things you have to make. And on the other side, you have to have the cavity formation. So in all these substrate related parameters, one thing is quite sure here: if we are making the cavity using an isotopic etching, then the silicon actually should be 100 orientation. Otherwise, it will be then you have to have some alternate processes which can be based on I will say that non-conventional machining techniques. So which can be used, but again, actually, it will add to the process cost. But to mention over here, we can use reactive ion etching, deep DRIE, deep reactive ion etching also. And we can also use USM, ultrasonic milling process also we can use. And but actually, in fact, this will again make the process costly, and the advantage actually will not be much, because the quality of the shape which we can bring through anisotropic etching control is at atomic scale level, which is not possible in other techniques. But in anisotropic etching, to make these cavities, there is a shape limitation is there. You can make only square or rectangular cavities. If you want the circular cavities, will not be possible using an isotopic etching. So these are the things, and we can actually have the performance of the device which is based on this cavity, because if we are making a circular cavity by let us see by USM, then the uniformity of the diaphragm on the entire diaphragm actually will be questionable on the edges. And in the sensor performance, the placement of the two resistors on the edges actually they play a very critical role, and this has the direct actually effect on the performance of the device. So these are the things actually you have to have to decide in advance that in what way you have to take up the whole process. And these are the variations. Here actually, as I have mentioned, that if you are having the diffuse resistor, the performance will be quite different. And you have to have, because the shape of the resistor, which will be defined in the crystalline silicon, as we know through the microelectronics, that actually that will depend on the diffusion coefficient or how the impurity will be diffused, and whether it is one-sided abrupt junction, or and how much actually it has been deformed from the actual shape from the window opening on the front surface. So these things actually we have to take into account. But in case of the polysilicon, which is outside the diaphragm, we can actually control the shape of the resistance very well. As we know that the placement and the shape of the resistors and the resistivity of the active layer, these are very, very important aspects and can be done by different routes. Okay, next coming to this, actually this is the main slide, that's why I'm spending more time here. In case of, can you go back please? Yeah. Yes. So in the piezoresistive pressure sensor making, how we are making the sensitive film, if it is not diffuse resistor based, so how we are making the layer which will be used to make the sensitive sensors piezoresistors. So it depends that how we are making. LPCVD polysilicon is one way. Similarly, physical vapor deposited polysilicon is another way, and MBE, molecular beam epitaxial growth of the of the active layer as we do in the SOI kind of substrate. So this is the ready-made substrate we purchase, and the cost is quite high. So these are the technological routes. And here actually you will see the technology, this temperature coefficient of these resistors, if we are doing using LPCVD or by doing the physical vapor deposition, quite different. Because the grain size and other things actually they play a major role. I will briefly discuss this thing in this talk. So as we know that piezo resistors, generally we use either polysilicon or crystalline silicon. So crystalline silicon we are using by making the diffuse resistors. A boron doped is done to enhance the piezoresistive coefficients. So phosphorus is not used in general. And when we talk about how to dope the boron, then either ion implantation or thermal diffusion. Similarly, as we know that in microelectronics, the ion implantation gives us very controlled profile of the boron, and that's why we can give a highly repeatable results of the resistor's value on the diaphragm. But in thermal diffusion is a process, and we have to compromise the accuracy or repeatability of the resistors over the entire wafer area. So these things actually they play or they have the direct influence of the performance of the device. Then, as I mentioned earlier, the diaphragm making is also where the different techniques are used, and these techniques play a major role on the performance of the device. Next slide, please. So this is particularly to explain that how diffuse resistors actually is used to make. So this is from the Z's book. You can see. So I thought that I should recall that how diffuse resistors are isolated from the high resistivity substrate. So we make very highly doped here, and this is low doped, of course, substrate. That's why it is highly resistive. And then step junction, which is boron doped, so it works as a isolated resistor over the diaphragm or whatever is the structure. Next slide, please. So this is a two-dimensional structure. The whole slide is not actually relevant, but I wanted to see that how this P plus and we cannot avoid this side diffusion. So we have to keep in mind that our resistors actually will not be, of course, if it is through ion implantation, even then by annealing process, certain dopants actually certainly will diffuse in the site, and this actually we have to keep in mind. Next, please. So here actually, basically, if we choose three types of substrate, so basic silicon is 100 in all the cases. This is the base material. But in this case, where we use silicon only, whether it is N-type, P-type, what is the resistivity, we are not bothered. So this is good to make a polyresistor type of resistive component for sensing application, and then we can go ahead with that. If you want to start with the N-type or highly substrate, then actually here in this case we can have diffuse resistors. If you want to make a diffuse resistor formulation or diffuse resistors version of the pressure sensor, we cannot use simple silicon 100 substrate. We have to optimize that what should be the substrate, and that's why in case of the diffuse resistor based Mams pressure sensor, you have to have highly resistive substrate 100, and it should be N-type, because then your resistor actually will not be isolated, and crosstalk will be there, and performance directly affected. And now the third substrate actually, if we are using the silicon 100, but over that oxide, very high quality oxide is there, and very high quality crystalline silicon layer is there of required thickness, of course. So these are the commercially available wafers called SOI wafers, and in industry, that's why it is very popular that people actually always talk about SOI-based processes, because active layer and the insulating layer, it is actually already developed, already provided, and very high quality of process like MBE has been used. So control over the resistivity and control over the quality of the oxide, actually it is already ensured. And that's why this SOI-based fabrication process is very popular in the industry because of the repeatability. And uniformity, also the yield will be very high in this case. In other case, where the resistor value and its uniformity on the entire wafer area, because wafer size is always increasing. So how we can make a uniform resistance over the whole surface? So questionable here in the above cases, but in the SOI case, it will be ensured, and this is the reason. But the cost actually substrate is quite high. It cannot be a low-cost process, though process steps are not crucial. But still, if you are having a layer, for example, if you are having a sheet active layer more than what actually you require. Suppose we want 1 micron thick active layer and it is 2 micron, and we want to reduce to 2 micron. So it will again actually make some complications in the process. So availability of the required substrate in the market, again, I will say, so this will be a challenge. If you have a process, industry process, then you have to have a pact with the supplier that the required material should be available during the production. So next, I will discuss briefly about the fabrication process actually. More or less fabrication process, not very different if we see. So actually in this process slide, you will see that diffuse resistors. So we will start from the silicon 100, then thermal oxidation is done, and it will be done on both the surfaces. And then coming to this, we will open the window and make the desired diaphragm thickness and the opening of the window also according to our design. And then from there, we will open the window for the resistors making. And we will do some boron doping selectively to define our resistors in the substrate. So you can see here that those resistors will be the part of the diaphragm here. So in this figure, though it is not there, but here actually when we do the boron doping, so resistors will be formed here in the diaphragm, and it will become the part of the diaphragm actually. There will be the stress, and these resistors will also be, and they will have more sensitive also because they are the part of the diaphragm, and that's why under certain applications, this is a requirement that the resistor should be the part of the diaphragm. And I'm just giving the hint that it gives the required noise level actually. Noise level is quite low here. And then further process for metallization, taking the contact and other things, they are same. But here actually, when we talk about the diffuse version of the Mams resistor, means we are making the resistors by doping process here. And that's why this silicon substrate, what we take in the beginning, has to be decided very carefully. It should be highly doped N-type substrate, and then actually we can make the diffuse resistors here at this stage, because in the process we are not actually making an isolation process for the resistors. Only PN junction actually will work actually as an isolation tool to make the resistors independently from others. So next process, please. Next slide. Here, when we talk about the polysilicon-based resistor, so here polysilicon-based resistor means we will start with the silicon substrate, and here silicon substrate may be N-type, P-type, or moderately doped, or whatever, because it is not going to affect our further wear. Only this will be act to make the cavity. So we will make the cavity from the on the other side, and cavity will be formed. I'm not talking about that process, how to align actually the cavity with the placement of the resistors, because this is not the part of this. Here, my concern is totally that how what are the technological variants, particularly in defining that if it is diffuse resistor based or polysilicon resistor based or SOI based process. So how actually we have to take the care of the process, and how the process will be different. So here, no need to worry about that. What is the silicon material? But it should be 100 because of the cavity, because we have to use the anisotropic etching. Even if we don't want to use this anisotropic etching, fine. Then you can use any material actually, because this material is going to have as a supporting material to give you a membrane over that, and that's all. It is not going to directly have the effect on the sensor performance. So here we are making the diaphragm here. After that, we will deposit the polysilicon layer over the oxide. So violet color layer, actually you will see it is a polysilicon layer. So polysilicon, here again variations. The polysilicon can be deposited using LPCVD. An LPCVD process, you know that it is moderately high temperature process, 620 or higher temperature. It is so because nothing is there to worry for that those layers actually will be affected by this temperature. But polysilicon is deposited by LPCVD, and it can also be deposited here. We can have two routes by physical vapor deposition. So LPCVD and electron beam, for example, what we have developed, and so here depending upon the requirement. So these two processes actually we have to decide here. After that, we have to dope it because we want the required sheet resistivity of the polysilicon film, so that the required value of the resistor is obtained. And this was also very important for the other processes also, that if we want 1 kilo ohm resistors, then we have to use the thickness of the film and the resistivity of the film, so that actually we should have the required resistor of given dimensions. So after defining the resistors, so we will do the lithography, and the resistors actually will be defined. Of course, shape of the resistors and placement of the resistors are also important, but that is the design part. I'm not touching over here in this talk. So once actually resistors are defined, the rest of the process is taking the metallization and content and other things is same. So this is clearly, you can see in this picture that the sensitive resistor or piezo resistors, they are sitting over the diaphragm and over the oxide also. So there is a separation. This oxide we have locally grown here, and this oxide actually going to be the part of the active device. So here actually cost not very high as it will be in the SOI, because in SOI oxide actually is ready-made available there. The high quality oxide is grown in the MB reactor, and that's why actually it's a big wafer and you have to use it for the fabrication. So after this, the whole process will be same. Next. So in SOI, as I mentioned earlier, when you take the SOI route of making the sensor, then you have to have the silicon 100 substrate, of course, and this is the ready-made wafer actually. Oxide layer is also there in bit, and the top layer is the active layer. And this active layer, as a matter of fact, is the layer of the of silicon, crystalline silicon, of course, of required resistivity and thickness, so that when we make the resistance of this layer, then actually the required resistance of the of that resistor will be obtained. So this is the stage actually, if you go back and recall that polysilicon, we deposit it and then we doped it. Here doping is also already available because required resistivity of the active layer is there. And the quality and the thickness of the oxide is also there. Only we have to do the lithography and we have to have the patterning for the resistors. So here in this slide, some more extra processes are also there, thermal oxidation. But thermal oxidation is not required if you have the right kind of SOI wafer with the oxide thickness, with the active layer thickness and the resistivity. Then that you don't need to have these steps which have been shown over here. Next slide, please. So once we have this kind of thing, whatever process actually we have defined, this is to reduce the thickness of the top layer, because actually we wanted 1 micron thick and it was 2 micron thick. So we actually had a process to remove the layer so that it is 1 micron everywhere. And then actually so after that, we have to have the process to making the cavity from the backside, and in this case again we have used the TEMA process. And then we have to have, next slide please, the patterning using lithography, and then active layer has to be etched out selectively to define the resistors of that active layer which was on the top. So this process, as a matter of fact, is a simple process, and if the SOI wafer is of required specifications, then only 4 or 5 processes are there, and you can make the whole thing. And this is going to be very industry compatible, and repeatability actually will be very high here. Next, please. So I hope that I have given some introduction of these variations. Next, please. Next slide, please. Yes, actually. Now you can see that these are the pressure sensors actually made. The first row is the diffuse-based resistor. So this is the chip and bonded, and these are the more chips. In the development work of all these resistors, actually, there was a requirement from the user agency that it should be glass bonded. So I did not talk about this because this is the common to all. So we developed a anodic bonding machine, and then this is a local anodic bonding machine, and it was very much used in developing this sealing process of the cavity from the backside. And here also I have not discussed about that what the location of the resistor and what was the shape of the resistors, because shape of the resistor and the location of the resistor over the diaphragm, this also actually make a direct actually connection with the performance of the device. But in this case actually that is not relevant to the title of my talk, so that I'm not going to discuss, but these are the practical things like what we have developed for diffuse resistors, for poly-based resistors, and for SOI-based resistors. Next, please. Next, please. Here, time is over, I think. Huh? Hello.
No, we have time. You can take extra time, no problem.
Yes, sir. Next, please.
Yeah, I think slide is not moving.
Some problem is there.
Yeah, slide is not moving.
Oh. So I have not used much more slides, eh?
Okay, no problem. Let me try another way.
Okay. So actually in this, if any question, please, from these technological aspects. Yeah. So can we go quickly, because this we have discussed, so I'm not going to to say more about it. Yes, this actually everybody knows that how to do it, and this is the Next, please. Yes, this is the performance actually of these three type of versions of diffuse version, This is poly version, then diffuse version, and the SOI based version. So this is just to show you that the whole technology actually is true, and it can be made up to the end where packaged devices are tested for their performance. You can see the table given over here, but the performance of the device actually of the sensor actually they are very much related with which technology we are using, and we can tune the intermediate processes to get the desired specs of the sensors. So this is the beauty of all these processes. For example, you can vary the diffuse resistor resistivity and so on. And you can dope actually the required dopant actually where the piezo resistivity of the silicon substrate is higher. Today we know that boron dope silicon actually is having the higher piezo resistive coefficient in comparison to the phosphorus dope, and that's why boron is generally used to define the piezo resistor substrate in silicon for sensor purposes. And this is technology compatibility is also there. So this is also important aspect. Next, please. Can we go to the next slide, please?
Yeah, sorry, it is taking some time.
Yeah, this I wanted to say that. Okay, next, please. Yeah. Next slide, please. So actually, how to design actually the piezo resistor dimension and other thing for the given value. So here actually why I have taken this, because I wanted to show that what is the role of the technology here. So here actually in this simple equation which everybody knows, rho s is there, R is equal to rho s and this. So rho s is the sheet resistivity. And this sheet resistivity actually we control this from the doping. So what I talked that what should be the resistivity of the active layer. So if we are doing using the SOI substrate, then it is already actually done as our specifications were clear. So we purchase the wafer from the market of the given resistivity, and so we have the sheet resistivity as because we are purchasing from the market. But actually, how we control this heat resistivity in the lab. So in case of the diffuse resistor, and in case of the polysilicon based resistors, here actually we can optimize we can optimize the doping process to get the for example in this case 50 ohm per square or something like that, and accordingly then we can control that the exact value of the resistor, because the value of the resistor of the Wheatstone bridge configuration, this is also important to have the required performance of the sensor. So here actually my opinion was that how the technology coming here actually. So here we have to see that how to get the required resistivity, because we are using the doping process and so on. Next, please. Next, please, because this Wheatstone bridge performance everybody knows how to get, because on if we place the resistors on the compressive stress and the tensile stress, so I'm not going, because this is the design part. I'm talking about the technological part. Next, please. Yeah. Dr. Baruah, next, please.
Yes.
Okay, next. So here actually this slide gives some simulated results. We did very long time back, and to show that some kind of fringes of tensile and compressive state, they are there on the edges of the diaphragm when it is under the stress and of pressure and with different thicknesses. So this is the design part. So I'm not covering this over here. Next, please. Yes, next, please. I shall omit this. Next, please. Next, please. No?
No, there is a slide. It's taking some time. Maybe just do it.
It takes some time, right?
Yeah.
Anyway, yes.
Yeah. It's good.
This is the typical slide for how electron beam is used to deposit the polysilicon. And this is a published work from our group, and this polysilicon film actually later it was doped using Baruah, and then the sheet resistivity actually was controlled by doping process, and it was used in making the pressure sensors. So variation in the technology, either you are depositing polysilicon film by LPCVD or CVD process or PVD process. I call it PVD process, the physical vapor deposition. So both ways actually we can use. And here actually we have found the TCR value of PVD polysilicon was better actually. The performance of the device from the temperature point of view, it was better than the LPCVD. And because of the grain size, I will show you some studies we made on polysilicon also. Next slide, please. Yeah, next slide, please. Yes. So, yes, next, please, because this is. So actually, the purpose of mentioning this, that because polysilicon play a very important role in piezo-resistive pressure sensor fabrication in one type of version, what I have mentioned earlier. So we can actually tune the properties of the polysilicon, including its piezo-resistive coefficients, by controlling the grain growth and at different temperatures, and what is the grain size. And we can also make the study that where actually it will give the more stable performance. So some of the and this is the actually window where actually we can tune the properties of the final pressure sensor. So how the technology actually is going to bring a change in the performance of the pressure sensor. So this is the purpose of this study, that polysilicon, when it is played as a piezo resistor with thin film, then actually we can have two routes, for example, LPCVD and physical and PVD, and after that we can also dope the boron either in ion implantation or by thermal diffusion, and then annealing process also actually will make a change in the grain growth also. So these are the aspects where actually we can tune the performance of the pressure sensor on the basis of the properties of the film, which is going to be used to realize the piezo resistors. And so this is the purpose, that these are if we use the SOI process, everything is ready-made and coming from the from the commercial market. We cannot do such kind of studies in the crystalline silicon in the SOI substrate. But actually, if we use the polysilicon route, it will be cost effective, and we can also bring it, or we can also tune the properties according to the performance, what performance we require from the device, and we can have a different processes for that. So this is the beauty of polysilicon, and that's why polysilicon actually it is the requirement that a comparative analysis of the devices by changing the technological change actually in this area is very much required, and we can perhaps actually predict some pressure sensor of very high sensitivity also. Next, please. Here, actually, particularly in this slide, you can see if LPCVD polysilicon is deposited over the insulating substrate or silicon substrate, it makes a lot of difference on the grain size. But certainly, in this particular case, we need to have the isolation of the each resistor so that the crosstalk should be minimized. That is the requirement, and that's why either silicon dioxide or silicon nitride or the combination of both should be there while depositing polysilicon. Here, actually, you can see that in the first slide how the sheet resistivity of the film is controlled. Boron implantation, and this is the phosphorus implantation. So at 50 keV low electron volt, the phosphorus actually were implanted in the 0.5 micron LPCVD, and it was annealed 1000 degree for 40 minutes. So this very amazing data actually. See, in one case, for example, in case of phosphorus, the sheet resistivity, of course, decreases with implantation dose. Of course, this is very good because implantation dose actually is first is 1 into 10 power 15, and then this is 5 into 10 power 15. So if the higher actually impurities we are producing, then the sheet resistivity will go down, of course. But in case of the boron, there is slight up there. You know why? Because in case of the boron doped grains actually of polysilicon, this is phosphorus doped grains. So the effect of the grain actually, the grain growth actually is reversed in these two cases, and that effect is coming over here. So this way, and when grains, there is a change in the grain size, so this will bring a change in the piezoresistive coefficients of the film. And so we can actually tune the performance of the piezoresistors by varying the dopant or doping species and the parameter of the unimplanted dose. So this is the purpose of showing this, that we can optimize and we can tune the property of the performance of the final device in this way. Here in the second slide, you can see that this is not implantation. This is a thermal diffusion. So by thermal diffusion, you can see here because the temperature is there. So in both the cases, in phosphorus and boron, and this is the variation is that poly is on silicon and poly on nitride. So when it is on silicon, so it gives the lower heat resistivity, and when it is on insulating substrate, then actually it is separated from silicon, isolated. So the heat resistivity is bit higher in both the cases. Either it is phosphorus doped or boron doped. So generally we do the boron because of the piezoresistive coefficients. But this study we knowingly actually we did to know that what happens to the electrical performance of the layer when we use different doping species. Next, please. Okay, so this is the whole work actually in these 2 or 3 slides is how the technology comes in between in the design. When we actually want a resistor of a particular value having the particular dimension, then there is a technology involved there, how to control the sheet resistivity. And these works actually is that we can control the sheet resistivity of the active layer by doping process, by annealing, and so on. So this is quite actually clear here, that if we do that this temperature annealing process, if we do, then sheet resistivity actually comes down. And this is very much clear over here in all the cases. The three cases are this is the boron dope, then oxidation, and then annealing process is there. But if you do the this temperature actually variation is there, then the sheet resistivity goes down. And at higher temperature, if you do for example, boron doping, the black one. So if you do the boron doping at 920 degree, or if you do at 950 or 70, then 1020, and then 1080. So you will see that the sheet resistivity of the layer actually comes down. And in all the cases, whether it is oxidized or whether it is pre-annealed, even then actually if we do the doping of boron, then it comes down. So there is a big difference, but sheet resistivity comes down. And if we require the 50 ohm, then this parameter will be used to get the 50 ohm per square, and then we can accurately have the resistor value. Of course, because the process actually is done. So here some kind of deviation from the exact value will be more here in comparison to the SOI wafer, of course, because there everything done in the in situ chamber where the basic actually growth of the silicon material is done. So there everything is in a much controlled way, and the required resistivity can be obtained there very well. But this is the route where actually we can tune, and then we can actually have a different performance of the device also, because of this technological aspect of this sensing film. Next, please. Dr. Baruah, next, please.
Yes, sir, it's coming.
I think I have taken more time, but
no, it's okay, sir, because students do not have other activities now,
okay.
so
Next, after
we can take some extra time.
Okay. So actually, the purpose of showing all this work is that technologically, actually, we can bring the required changes in the active layer, and particularly this one, you can see that when we do the annealing of the polysilicon film at different temperatures, then the grain growth actually mechanism, which is called the normal grain growth mechanism. So where undoped polysilicon is annealed at different temperatures, and this is the unannealed as deposited polysilicon is also there. So this dip in force distance spectroscopy using AFM, you can see that this dip gives the information about the surface energy of the grain. And this surface energy of the grain actually has direct relevance to the piezoresistive coefficient of the film. Because in polysilicon, if we compare with the crystalline silicon, so in polysilicon, the piezoresistive coefficients actually, for piezoresistive coefficients, the grain actually size and the grain surface energy is also one of the extra parameter which is not there in crystalline silicon. So this way, perhaps we can have a tuned performance actually, varying performance of the device by choosing these routes, and we can bring these things to have the desired performance of the pressure sensor. Next, please. Yes, so this is the same for the same previous profile. This is the grain growth. If you see that as deposited is the left corner above, and the next is after annealing at 920 and 30, then you can see the cluster formation of the grains is started from here, and then elongation effect is there at 1000 or 1020 and 1070. So this is the ultimate grain size you can see, which is equivalent to the film thickness. And this is called the normal grain growth mechanism. It is not affected by the dopant because doping is not there. This is as it is. If we do the polysilicon film as it is without doping, and then we do annealing, so this is the change in the grain size, and and this is quite stable actually. For example, elongation. If you make the piezoresistive resistor of this polysilicon film after boron doping, then perhaps the piezoresistive coefficient will be different. And this stage will be quite interesting, that we can have the desired piezoresistive coefficient by varying the grain growth by the grain size. So this is a clear indication that if we have the grains either in cluster form or elongation form or final form. So if we use these as a basic initial polysilicon film, and then we do the doping of boron, and then we measure the performance, certainly it will be different. So these are the possibilities. We can introduce the technology in tuning the properties of the pressure sensor by changing the piezoresistive coefficients. Next, please. Okay, so this is a typical profile of polysilicon-based piezoresistors, where actually you can see that it can also be a temperature sensor along with the pressure sensor. And here actually this complete performance actually has been shown here. Then that the same chip can be used as a pressure sensor as well as vacuum sensor if sucking is there, and you can see the slope is same almost on the, but there is a gap here, jump here, when it jumps from pressure to vacuum, so it starts from here. So it may be due to the setup actually we use for switching from pressure to vacuum, because we wanted to see that how actually it changes when we apply the vacuum and when we apply the pressure. Okay, so multifunctionality also is possible in these pressure sensors, and that also can be changed actually, can be tuned by changing these properties of the film, and film is very important. Piezoresistive coefficients are related to that, and the placement, this is the design part, and the cavity formation also, because how accurately cavity edges are there. So these are the important things, and they bring to direct relevance connection to the performance of the device. Next, please. Yes, sir. Okay, next. Yeah. So this is a typical, because another aspect is how we are making the cavity. So you know that this right side of picture, this is the circular cavity made by DRIE, Deep Reactive Ion Etching. As you know that by anisotropic etching or using tetramethyl ammonium hydroxide or KOH, we cannot make the circular diaphragm. But if we want to make the circular diaphragm, then we have some alternate etching techniques. So here on the left side, you can see the two pictures. One is the arrays of the cavity, and one is the enlargement of one of the cavities here, made by ultrasonic milling process. And you can see that the finishing of the walls are still, but some finishing is not that much as in case of DRI, where we see here. But actually, if it is followed by some laser kind of finish touches on the edges, it is improved. But we have made the device and it worked very well. So you will see that in making these devices, these cavities by an isotopic etching, so it takes 9 hours or so. But if you use the USM or this kind of techniques, they take very little time, even in minutes. But the sample preparation also consumes a lot of time. But these are the things, and we can bring the technological changes in the process. Next, please. Baruah sir, next, please. Okay, next, please. This is something else. Yeah. So these are some. See, this is one of the device which is very, very small, and here the chip actually we are looking before. So this is there are 9 chips here, and that was the single chip. So very small cavity can be generated by these techniques. And I remember this device actually was developed again. Actually, one trainee from Tezpur University was involved in the beginning, and we started this work, and then we developed the whole chip. Actually, and this is very micro chip actually, and so miniaturization in this kind of thing is also possible. But again, making the cavity here over the membrane, I will call it membrane because this is silicon dioxide and silicon nitride membrane, and then after that it is sealed. So cavity is sealed. So this is called the absolute pressure sensor because now it had no connection with the outside world. So it will be used as absolute pressure sensor. So these kind of small, tiny pressure sensor chips can be. But in this case, you will see that the formation of the resistors. So these 2 resistors are sitting on the diaphragm and 2 resistors are outside the diaphragm. So this is half Wheatstone bridge configuration. But if we have the technology where very small dimensional structures can be made, so possible. So this is, next slide please, yeah. So this is another way how we can make the realize the cavity by top process only, nothing to go out otherwise. So if we can have the holes and then the whole cavity can be made and the resistor can be applied over here, and how Wheatstone bridge configured structures can be realized. So this is the theoretical work, and some work actually was done, but it is possible to have such kind of tiny devices with very small cavity size. Next, please. Yes, in anisotropic etchant, so you have to have the that what kind of surface of the diaphragm you want, whether it should be rough or it should be very flat and very finished surface. So both have performance, direct relation to the performance of the device, and you see that if the concentration of this is particularly for the KOH, which is toxic, but if you use the 10% weight of KOH or some other percentage of KOH, so you will see the difference that the etching surface will be affected by the etchant. Similarly, in TEMA also, if the temperature and the concentration of the TEMA is not proper, then you will have a different type of shape. And according to the application, we can choose that what kind of etchant actually if we had to use. TEMA is most recommended because this is non-toxic, and it has simple process for masking because silicon dioxide is work as a mask, but in KOH silicon dioxide does not work as a mask. It has to be actually masked by silicon nitride over silicon dioxide. So the process is quite actually complicated. So KOH based etching is not accepted, but TEMA is accepted. I will talk it. So thank you very much for this slide. And here actually I would like to acknowledge the support and very close collaboration with the this ED section, electronics division of BRC, and this actually variation on the substrate what we have presented here or discussed here of diffuse version or polysilicon version or SOI based version. Actually, this was the activity launched by BRC, and we contributed here. And I found it a very good research area where actually we can do more work, and we can do that how the technology actually impacts the performance of the device, and I feel that this area is still actually to be explored. That how the performance of these devices actually are crucial based on these technologies. Some work, of course, BRC team actually they reported, but actually we found very practical experience in this. Of course, CSR series facilities were used there, and we were having the complete facility. And team at CSR series contributed a lot in developing of this device. So I would say that as far as is the concern of the fabrication process of Mams sensor, it's okay. But along with that, actually, we have also to find out that which technology is compatible to our industry, and so that the dependency of other factors or other countries should be minimized, and we should develop the process which is more actually compatible with our industry requirement. So this aspect of technology variants actually in making a single device, I feel that this also actually very important to be looked into. And polysilicon piezoresistive pressure sensor is a very common device. I remember it was developed in 2000, but actually consistently working in this area. So very innovative actually contributions actually we made, and now still actually we feel there is much to add in this area and develop the pressure sensors of different performance and for different applications also. As I mentioned earlier, that packaging and the interface electronics, very important aspect, because sensor chip development is one area, and packaging development and the interface electronics, and all this for a particular application. This makes the whole thing actually the complete activity. If we do only one, then it will not be acceptable by industry. The complete solution will be the chip fabrication, chip design and fabrication, and then packaging, and then the interface electronics. So I hope and I encourage youngsters, actually young people, they should come forward and let us take a lead in sensor development in the country, what I feel. Because this can be done, actually, what I feel. But we should provide the solutions actually to the industry. We should make the prototypes and show it that how it works. Now actually these bulk devices are going to be obsolete. Then flexible electronics coming, then very small devices are coming. So if we don't speed up our work, then actually it will be difficult to pace with the advancement in the technology, what I feel. So I also still feel that this is an area where we can contribute innovatively. So thank you very much. And if there is any question or clarifications, please.
Okay, thank you so much, sir. So you have described so elaborately, and I do also remember when I was working in your lab for a few days, some of the processes that you innovated, for example, TIMA process and all that, lab, and today it is a brush up for me as well. So we have lots of questions actually from students. So with the interest of time, maybe I will take a few of them. I will read for you, sir. Robert from East Africa, his question is, what is the difference between piezoresistive and piezoelectric sensors?
Oh, so I have not covered here piezoelectric.
Yes.
So the title of the talk was totally focused on piezoresistive based pressure sensor. So as one line was there in one of the slides that piezoresistive means when there is a pressure or mechanical force, then there is a change in the resistor value, electrical resistor value. So in piezoelectric, actually, of course, after getting a mechanical force, so then voltage is developed, and some electrical signal is developed, and that can also be used as a sensor. But piezoelectric property, for example, if we have the sandwich structure where the charge has to be collected or charge to be sensed actually directly. So this is the major difference of piezoresistive and piezoelectric, of course. So, for example, in piezoelectric type of thing, we should have the kind of change actually in the structure where it is kept under the electrodes which are conducting, and voltage is measured. And vice versa also actually. Piezoelectric property is reversible process. So you can also have, but piezoresistive property is not reversible. It is irreversible. So this is the thing actually immediately came to my mind. So yes, please.
Okay. Yeah, another question is about isotropic etching and anisotropic etching. So how they are used in different processes.
Can you repeat, please?
Isotropic etching and anisotropic etching. So how they are used in different processes. Maybe his question is, what is the difference?
Actually, an isotopic etching of silicon is the backbone for bringing this MEMS technology actually. And an isotopic etching this is not uniform etching in all the directions. If we suppose in silicon, if it is crystalline silicon, so planes are there, and across each plane actually the etching rate in a particular solution, for example, not in all solutions. So etching rate of silicon is different. So I have not touched this knowingly, because otherwise it would have become a separate talk. So in anisotropic etching, when we talk, then it means here in this particular MEMS technology that the atomic planes of the material, across those planes, the etching rate is different. For example, if I take 3 planes of silicon, 100 oriented silicon means 100 phase, 110 phase, and 111 phase. So if we see the etching rate of silicon in KOH, for example, is if 1 in direction of 111, then it is 400 times across 100, and it is 600 times across 110. So this is the beauty of this anisotropic etching, because planes are atomic planes. So if we open the window, and which is aligned with these crystal planes, then we can control the cavity dimensions at atomic scale. This is the beauty of this anisotropic etching. But you have to have alignment of that pattern of that window, because crystal planes are not visible. Only we are having the principal cut, secondary cut on the silicon wafer, for example. So we have to be careful for this, that where is the cut. And that's why in Mams technology, these principal cut, they have very important. Their importance is more in Mams technology than in microelectronics. Similarly, this in microelectronics, actually, this crystal planes, they play roles in deciding the electronic properties, for example, in CHAN and other things. But in Mams technology, when we talk about an isotopic etching, then in making the 3D structures, so this is very important. If we use the isotopic agent, again, for silicon, there are isotopic agent. You can use this HNO3 plus HF and acetic acid kind of combinations of, or HF HNO3 solution, 1:6. There is a rate. Here actually they etch the silicon in with the same etching rate in all the directions. This is one thing. And so we call it isotopic agents. So for silicon, there are separate anisotropic agents, for example, tetramethyl ammonium hydroxide and KOH, aqueous KOH. And silicon dioxide works as a mask if it is tetramethyl ammonium hydroxide, and if it is KOH, then silicon nitride, LPCVD silicon nitride, works as a mask for selective etching, of silicon. So in Mams technology, making the controlled dimensions cavity, we use the anisotropic agents. And this is the backbone of Mams technology, I will say.
Okay, thank you, sir. So another question is, what is LOD of these kind of sensors? How do you optimize the thickness of the diaphragm? Also, he's asking, with thickness, how does the sensitivity vary?
You have to repeat.
So
again.
basically, he has three questions. I will read it again. What is LOD of these sensors? How do you optimize the thickness of the diaphragm? And with thickness, how the sensitivity vary?
Actually, this is again how we control the thickness of the diaphragm, and this is quite interesting. This is the process actually. Generally, people use the etching rate, which is not proper. By reactive ion etching, also actually when they use deep reactive ion etching, there also the etching rate is there. But actually, we have developed a very accurate process. See, in the Mams wafer, if it is 2-inch diameter or 3-inch or 4-inch, on the edges, we make certain holes, and there is a pattern for that. And we do prior etching on these hole sides first, and then actually the diaphragm etching is done along with these etching actually what we have done earlier on this hole side. And when holes are open on the edges, then the required actually remaining diaphragm thickness is obtained there on the diaphragm. And this technique actually is quite simple, and it works. And that's why you might have seen that in all my wafers there are 2 holes on the edges, rather 4 sides. So and there is a meaning of 2 holes because it also works as a alignment mark for the later processes. So the control of diaphragm dimensions actually, if we say XY plus the thickness. So thickness is controlled in this way by utilizing the uniform, and that's why it is reflex condenser is used in anisotropic etching processes, because the concentration and the concentration and by condensation the water vapor back to the solution is maintained, and the temperature is also maintained. So this simple process of reflex condenser with the hot plate arrangement, this plays a crucial role in maintaining the etching rate constant. And because etching rate in KOH or in ATEMA, it is some micron per minute actually, maybe 0.7 micron per minute or 0.8 micron per minute or 1 micron per minute. So is 1 minute is a time actually we can also check while taking out the samples once or twice in the whole process. And as you know that 0.7 micron or 0.5 micron per minute is a very slow process. And if you consider the 2-inch wafer, the total thickness of the wafer is 300 micron. So in etching, the 250 micron, roughly, if you want to make the 50 micron diaphragm, so you can think that 7 to 8 hours or 8 to 9 hours actually are required. So it is a long process to be done. And that's why in the batch fabrication, number of wafers actually are suggested to be etched simultaneously. And the full batch production of this cavity formation can be done. And that's why these two holes on the edges actually, they also works as an endpoint detection actually points. And this is a beautiful process to control the diaphragm thickness. As far as the concern of the XY dimension of the diaphragm, so this is again actually when you open the window for the etching, then how accurately you have aligned with the planes. So with the principal cut actually, if you keep in mind, then how accurately it is aligned, that will decide actually the ultimate dimension. Suppose you want to make a 2 mm by 2 mm, then there will be an angle between 111 and the 100 plate. So it will go like this. So you will have a broader window opening on the back surface, and after that it will be slanting like this. And when it is 2 mm by 2 mm exactly, so you have to stop it. So this is a kind of a skill, manpower actually is required there, and we have seen that it is very simple and very controlled dimensions of the cavity are obtained, and it is very important because on the other side the resistors are sitting. So if the placement of the resistors which are on the edges sides, so they should be, all resistors should be placed on the desired location as you have considered in the design. So this is done by keeping an eye over these process steps, and then you will find that beautifully actually you will see that we have seen it from giving the light from the back side and how the resistors are placed. So it is quite accurate process to control the dimensions of the cavity as well as the resistors placement on the edges of the cavity. Please.
Okay. So another question, probably last question I'm taking. How the flexible pressure sensors are different than the rigid, the normal pressure sensors in terms of processes, fabrication processes? Actually, here I will comment that whatever electronics we are doing, it is rigid electronics, I will say, based on rigid materials, so flexibility is not there, otherwise there will be crack or breakage and other things. In flexible sensors making, people are doing wonderful work actually. People have made pressure sensors based on paper technology. And you will see that there is a famous person who has worked notably on paper substrate, paper substrate. This as a substrate. And now, because paper technology is quite mature, so people are using this cellular paper-based technology in making number of devices. In flexible pressure sensors, people have
started making these devices using a spongy type of capacitive pressure sensors. When there are two electrodes and in between there is a dielectric. So in case of dielectric, they have used PVDF, and on the other on either side they have coated the nickel based urethane material, which is a spongy type on both the sides, and it works as a conducting film. And then the capacitance of this structure is measured, and there is a quite wide range, and this can be made of very small size also, and it is totally flexible because PVDF very thin material is there, and they have studied that how if the thickness of the PVDF is varied, then what is the range or sensitivity of this type of sensor can be optimized. So different new materials, I will say, which are flexible in nature, which are technological compatible, and which have more sensitivity also. So people are working on this, and whatever I have shared, actually I will say these are the recent papers actually I have reviewed, and I have come to know that people are working and people are doing on it. And so flexible electronics coming up, and we should, that's why I hinted that we should try to jump now for new materials for different applications, because our biological system is the ultimate science, and this is flexible. So we have to actually think about new materials, and so that we could sense, we could interface and other things. These things actually we should think for it. This interface electronics in today's form, what we see, perhaps need to be actually think over it, that how it will change the shape or the mechanism of interfacing the or data transferring or communication based on certain mechanisms. So these things actually, they are going to take over our so-called usual or conventional science. So, and this is very interesting actually. This is very interesting. People are doing some prototypes and trying to show it. So, good question for that flexible sensors people have made wide area.
So
wide.
We had,
Yes,
so we had many questions probably with the interest.
Yes. I will be very happy, but George Whiteside is the person actually who has done good work in developing the paper-based piezo-resistive pressure sensor. And he has done this work.
So here we are started exploring some theoretical work on flexible electronics. So we have some students working, so quite interesting. Probably slowly we'll try in the fabrication site. So I think, sir, thank you so much for your involving talk. We learned a lot, and many students are involved in fabrication here. So it will be very, very useful for them. So thank you so much.
Thank you.
We hope to get you again in near future. So thank you so much, and good night.
Thank you. Let me actually acknowledge number of trainees from technical universities. They worked with me in CSIR City, and I am really thankful to them. Also, they contributed a lot, and they also learned. I also learned with them. So.
Yes, sir, that is the process. I also got it.
Yeah. Thank you, sir.
I also got introduced to fabrication in your lab only. So thank you so much for guiding us, for guiding our students. So thank you so much, sir. Good night.
Thank you. It will be my pleasure if somebody wants to interact or by through email or whatever. So
Yeah.
Okay. Thank you very much. Thank you all.
Okay, sir. Okay, sir. Good night. Good night. So, all the participants, with this, let us conclude this session here. See you tomorrow at 4 p.m. Thank you so much.